Our second presentation for this session is from Jianping, and it's going to be about domain-specific languages for computational fluid dynamics. Please, Jianping.
Many thanks for your introduction, Selvan. So, my name is Jianping Meng. So, I'm a member of the Computational Engineering Group, which is led by Professor David Emerson in our Scientific Computing Department at the STFC Dasbury Laboratory. It's my great pleasure to be here to talk about our work on kind of domain-specific languages for exascale fluid simulations. So, yeah, my talk is roughly 5 parts. Yes. So, first of all, I will talk about the opportunities and the challenges for our current scientific computing, and then I will briefly introduce the concept of domain-specific language. And then I will try to update a bit on our progress for developing the codes following the domain-specific language approach. And then I will introduce about 4 use cases which are based on our development. Then finally, I will give our concluding remarks and outlook. Talking about scientific computing, we are really at a very exciting period. One of the highlights is that we are quickly entering into the so-called exascale computing era. Actually, we were talking about this concept maybe 1 decade ago. By exascale, we mean that a supercomputer provides the computing power equivalent to millions of laptops of our daily usage. I mean, so in the world, the first supercomputer achieved this aim is the so-called frontier computer, which is hosted currently at the Oak Ridge National Lab in the US. So I think its computing power is about 1.1 something exaflops. And actually, at 4 years ago, at the same lab, they also hosted the fastest supercomputer in that time. So about in 28. So just 4 years, we gain 8 times more computing power. So, and also this kind of computing power should enable us to conduct our numerical simulations or computer modeling at a much larger scale with better accuracy and perhaps within shorter period. In the UK, it's also a kind of a national strategy to deploy such a computer by 2025. So as claimed by Amanda Soloway, so the previous parliamentary under the secretary of the Department of the Base. So she wrote that for answering a question, so from the Chiova, the parliament member for the Newcastle upon Tyne Central, so that the UK research and innovation strategy is for the UK to deploy exascale supercomputer by 2025. So with such kind of computers, we could have transformative potential for researchers, industry, and the public sector. So the larger scale applications require investing in a computational infrastructure that including exascale supercomputing to enable the most challenging modeling and simulation problems. So that actually really is of vital importance to have the hardware and the software to effectively utilize the hardware. However, it's not easy to use this kind of new supercomputers. It is because that to gain computing power in a more energy efficient way, we have multiple purposes for this reason. One of the reasons is to get more energy efficient computing. So we tend to use new technologies in these computers. One of these examples is the so-called graphical processing unit. This kind of device actually has been used actually for computing gaming. So when we play computer games, in particular 3D player, so we definitely need a very high-end computer graphical card. However, I think it's about 2000 years. So people find actually we could utilize this kind of device for computation, for modeling. But this kind of device is in general different from our traditional device for computing, the CPU. So we need different programming technology for this kind of devices. And this kind of change caused major challenge for developing software to utilize these kind of devices. And actually, we don't only have one technology. So we could have also other hardware like FPGA for computation. Or we need quite a different programming technology from CPU. So just utilize actually, these two can still utilize this as an example. Even both computers are utilizing GPU, but if we look at it closely, we find that actually for the submit, we have 27,000 NVIDIA GPU cards, which we tend to use the CUDA software framework for programming. However, for the current one, it is the GPU card from AMD. Then again, so the software framework is different. So it's the so-called heap framework. So in theory, so we at least for get the best performance, we could still need to port the code, even we have the CUDA, the code written in CUDA framework. So actually, but this is definitely not an easy task. Even though the CUDA framework was released is about 2006, the major open source software, the porting work is still ongoing, for example, like OpenFOAM. So that how to tackling this big change and the challenge. So we believe that domain-specific language is one of the possible ways for this purpose. Technically speaking, domain-specific language follow the definition by this author, Martin. So it's a computer language designed for a particular kind of domain, rather than a general purpose language for any kind of software problem like C++. So by focus on one domain or one particular problem area, so we could develop very high-level things to cover the details for the implementation. And then developers or users can quickly do the software development for the purpose. For example, actually, the web pages we are browsing every day are built on one kind of domain-specific language, the so-called HTML. It's a kind of. Regarding the scientific computing, so our major aim is to enable a concept of separation of concepts. That is, the algorithm that encapsulate the mathematics and physics of the problem should be separated from the computational science of the implementation. Just to use GPU as an example, so we should enable our researchers or developers to focus on really how to implement the math for the physics, rather than every day focus on how to program in GPU or how to program FPGA. So that's the purpose. And also, we feel that for the domain-specific language, we at least need to provide these two properties. That domain-specific language must be easy to understand, and also must provide a very good computational performance. Otherwise, there's no point to use it. Okay, so yeah, now we talk about the fluid simulations. Fluid simulations is typically a mathematically complicated area. So we do have a number of methods to model fluid flows. The most established one is based on this equation, which was proposed by these two. One is engineering, one is physics, about 2 decades ago. So as we can see that, just at the first glance, we should feel that this equation is not easy. So we definitely need very advanced mathematical techniques to solve it in our computer. And later, actually, so we will say that based on domain-specific language, actually, we may also not only reduce the complexity in implementation on hardware, but possibly we could also help to hide some details for the mathematical solution for this equation. Another method is the so-called lattice Boltzmann method. This is a relatively simple to unstandard method. Basically, so the whole algorithm can be summarized by this animation. So basically, we get a number of particles. Then these particles move at certain directions, and then they collide or interact with each other. So then after collision, then they go away again. So the collision rule is specially designed so that we make sure that we could correctly recover or model the fluid flow. So this method actually looks at where the implementation side is very simple, but if we really want to prove it is correctly simulate fluid, actually it's quite cumbersome. So one of the route actually is go to the so-called Boltzmann equation, which is proposed by Ludwig Boltzmann, also at about, I think these two equations are similar. So Boltzmann equation is maybe 20 years younger than the Navier-Stokes equation. So that, so very cumbersome mathematical techniques needed, but fortunately in our implementations, it is really easy. And also such that this method is quite good for investigating complex physics because we can forget about some numerical things. So we are currently mainly involved 3 pieces of code development following this approach. So the first one is the so-called Oxford Parallel Library for Structured Mesh Solver. This is a DSL framework for us to writing code to solve complex mathematical equations. Then definitely it works for Navier equations, but not limited to. For example, I think the company NAG actually utilizes it for financial purpose. So the benefit of this library actually is that if we writing code following the DSL approach, then we just need to write the code once, and it can run anywhere, including like a GPU, various kind of software framework for GPU, like CUDA, OpenCL, OpenMP, OpenSCC, and also recently, so I think the OPS team added a heap. And the second piece of code is the so-called OpenCBLI. This is a DSL framework for generating C and C+ code that perform the finite difference approximation for mathematical equations. Again, so it can work for not only Navier equation, but also other one. Currently, so this library mainly depend on the OPS. So that means it will generate code in the OP DSL. And like we just mentioned, the things of this code is doing actually is help us to automatically generate a numerical algorithm. So for example, if we want to use a central difference scheme, then we actually don't need to look at detail. So we just ask the code, oh, we need a central differencing. So then the C++ will be automatically generated. The third piece of code actually is the so-called high-level mesoscale modeling system. This is a DSL framework for specially designed for lattice Boltzmann method. So major development also are based on OPDSL. Also, we do have some initial work on the so-called EPSRC library, which is for adaptation mesh refinement. So the benefit from the OPS side, so both these two code can have this property. So we just really need to code once. Then we can easily get the code to run many platforms by simply call a code translator. So in terms of OPDSL, so currently what we are doing is actually a piece of important work is try to promote the sustainable software development. This kind of approach is very important for any software engineering project. So for this purpose, so we developed the documentation system for the library, so which can help users to learn the code and also help the developers to understand the structure of the code and the principle we need to follow for the code development. So we also propose the working flow for integrate or to contribute to the code collaboratively. Basically, more technically speaking, so we have a standard, we propose the standard Git flow work approach to automatically, to collaboratively integrate the contribution. And also for this purpose, we developed the so-called continuous integration system. So once a developer develops some new capabilities, then if they submit the contribution, then the system can automatically identify if this piece of work can work smoothly with other part of the work code or not. If works, then we know easily here. If not, then we get across. So it's quite important for the software development. We are also developing the capabilities to write out a selected selection of the simulation data. So that is also important because sometimes we don't need to output all the data. We just need a section for them. So this kind of capability can greatly reduce the I/O workload. So we are also trying to look at some in situ data processing procedure like FFT to integrate into the code or linear algebra solver we are testing. For the OpenSBLI, so we implemented a kind of a new capability into the code. So for generating high-order compact finite difference scheme. So currently, so we finished the code for writing for generated code, and then we did some tests here. So for a simple wave transportation equations. So as we can see that we get a correct solution, and also the generated code again. So as said, so can just we did write the code once, then the code can automatically run on GPU and the CPU. So we are also trying to writing a script to help to make the workflow smoother, because for this kind of library, we do have some dependencies like HD5 or CMake. So that we are writing a script to automatically either load the CMake module in Archer 2 or install the CMake in your local system, then automatically by 3 simple steps, so that to make the users or the developers' life easier to use the code. The certificate code actually, so we are leading the development. So and this system designed for export method. So we covers quite a bit of the conventional capabilities, like for single phase flow, and for multi-phase flow, like here example of air bubble. Actually, the cavitation bubble collapse. As I said, because this kind of method is quite good for investigating this kind of detailed phenomena. So to help the users to writing their own code for their research, so we also have interfaces for writing user-defined functions. So next, we are looking at the performance of the DSL code. So here, I just show the high-level one. But OpenSBLI also based on OPS, so they share very similar result in this regard. The first machine we tested actually is the Archer 2. So I think here most of you will know Archer 2, so I will ignore really introduction. So Archer 2 actually is about 2% of the exascale computer, but still ranked number 28 in top 500 list. So we run simulations about 1,000 cubic lattice simulation. And as we can see here, so until 4,096 nodes, we still get superlinear scaling. So I think I cannot test more nodes. So it's a good, really good parallel performance. So it's about 500,000 cores. And also the second test is a multiple GPU cluster. So this is based on the N8 bit system, so which is equipped with NVIDIA Tesla V100 GPUs. So we run the weak scaling test in this case, And as we can see that until 16 nodes, that means 64 GPU cards, we can still get quite a good efficiency. So next, we are introduce our use cases. So the first one actually is based on OpenSBLI. So the simulation is done by Dr. David Lash at the Japan Aerospace Exploration Agency. So the simulation is conducted by using a multi-GPU cluster, so the so-called GSS3 supercomputer in JAXA. So I think this computer is ranked about number 39 in the top 500 list. So the simulation is about to simulate the so-called transonic Buffet phenomena, which is important for commercial aircraft. So because this kind of phenomena could cause lift and pressure fluctuation, which if we were on that flight, we don't want, I think. So that our developed new I/O capability for OPS and OpenSBLI greatly reduce the output data size. If we output all the data, it will be 4.25 gigabytes. But if we only output a selection data, because for this result, actually we just need a section of the domain. So that actually we only need to output 35 gigabytes, which is about more than 100 times of reduce. So that actually, if we want to download this kind of data in our home office from a supercomputer, which is usually the case, we could need a day long if your network not broken. So here, if we got a reasonable broadband, it should be very quick, maybe within 10 minutes. The second use case is actually about an undergraduate student project in University of Birmingham. Inside the aerospace area, or more specifically aeroacoustic modeling. So both OpenSBLI and OPS and HiLEMS help the student to conduct his project. With two codes, I think the student plan to evaluate the capability of lattice Boltzmann method by running simulations on the local supercomputers at the University of Birmingham. The purpose is that the two photos, because lattice Boltzmann is a relatively new method, but it was said quite good for this area. So this project is really, we want to have a look on the accuracy of the method. So yeah, this is with Dr. Zhongnan Wang at the University of Birmingham. The third piece of work actually also is a recent visiting PhD student project with Professor Shen Jipan in the Hydro Environment Research Center of Cardiff University. So in this simulation, this research is about to look at the design of a kind of new devices, the so-called oscillating water columns. So to harness the energy from the oscillation of the seawater inside a chamber or hollow caused by the actions of waves. This one work is based on HiLEMS, where when Mr. Bao Mingguo actually is here there. So to quickly implement the actual capability needed for the simulations and then speed the simulation for designing this kind of new concept. So yeah, here is a kind of dam breaking flow simulated by lattice Boltzmann method. So I think random sample is about 10,000. So the fourth case is actually about, it's very interesting, the so-called Fourier-impaired liquid diode. So by liquid diode, that means it's kind of similar to the electronic one. So that means the flow can flow from this side to this side, but it cannot flow in a reverse direction. So this is quite useful for the microfluidics design, because like with many applications like in biomedical and flow measuring. So actually, the starting point is here for female fleeing. So for this kind of the organ for storing sperms. So the fluid, the liquid carrying the sperms can only flow from here, the orifice to bladder and to HeLa, but it cannot flow in a reverse direction. This should be due to the complex interaction with fluid, liquid, and surface, like Laplace pressure gradient and surface tension, and also the surface geometry, the structure. So the boson is the Professor Halim's group actually at the Durham University, so was able to quickly implement their model based on Halim's, and then investigate the design of this kind of interesting things. To calculate, to tackle the challenge of the exascale computing, so we have been advancing the domain language approaches for fluid simulations. And to make the software development more sustainable, we proposed and promote some principle of software engineering during our development. And of course, we are also developing new capabilities into the code. And then the developed system and the capabilities are enabling our fluid research community to effectively utilize current and future computers. And also, in the next couple of decades, so I believe that we might see very exciting paradigm shift for our scientific computing. For example, quantum computing or like artificial intelligence. So the domain language approach could be still a good choice to smooth the transition process. Finally, let me give me thanks for all of our collaborators, because I try to summarize the result of a number of projects. So if I miss anybody, so please I'm sorry. Thanks for your attention, and any questions?
Thank you very much. Any questions for Jianping? No questions. One question.
So I was wondering whether there is any development of developing international standards for these domain-specific languages. So eventually we might have something like C++ or Fortran, which I could use basically everywhere.
Because it's because it's a domain for languages, so it's really we are focused on a small area. So even for fluid simulations, because we have different methods, so currently we have at least two different methods. So that it's really difficult for me to see if there's any international standard. But what I can say is that here, so the main development is based on C and C++ plus Python code translator. And we do also have some Fortran backend. So in the US, so we know that like a library like a CoSeC, so it's also based on C and C++. It matters because C and C++ provide some mechanism for code generation, because the domain language is quite strongly relying on code generation. So we either go to Python or go to the C++ template metaprogramming. So like CoSeC is based on C++ template programming. So that both are techniques actually, the behind the scenes is quite complicated actually, while we do provide users to reduce the users' complexity. Yeah. Thanks. Hopefully I answered the questions.
Thank you very much. In the interest of time, we are going to thank Jianping again for this nice presentation.